Welcome back to the deep dive. If you've been keeping track of the AI landscape, you probably know the big shift isn't just about bigger models anymore.
No, it's really about the agents that use those models.
Exactly. These large language model agents, they're moving past just being chatbots. They're becoming, well, the main way we interact with huge, complex data systems, kind of operating on our behalf.
And that's a huge shift, a fundamental one for data architecture. I mean, our current systems, built over decades, right? They're designed for how humans ask questions.
Predictable questions, targeted, not constant.
Precisely. But these LLM agents, they bring a whole new kind of workload to the table, completely different.
And we're calling this workload agentic speculation. That's our mission today, to really define this exploratory process and then unpack the four, let's say, critical characteristics that tell us how we need to redesign our data systems for it.
Yeah, these four things scale: heterogeneity, redundancy, and steerability. They're really the key.
Get the levers right. Get it right, and maybe we unlock massive productivity gains. Get it wrong.
And you completely swamp the existing infrastructure. It just won't cope.
Okay, so let's start with defining agentic speculation properly. What is it exactly?
So, put simply, it's a very high throughput exploratory querying process.
Hmm.
And you have to ask why an agent speculates like this. It's because it lacks what we call grounding.
Grounding, meaning it doesn't inherently know the data's layout, the schema, the columns.
Exactly that. It doesn't have that built-in awareness. It's like trying to navigate a massive complex warehouse in the pitch dark. You don't have the map memorized.
So you have to feel your way around.
Right. And because it can't see the map, the agent compensates by just, well, tirelessly trying out possibilities. It does metadata discovery, sort of checking the labels on the aisles, and it tries building parts of a solution, validates that, basically jiggling the keys until one fits the lock.
That sounds incredibly inefficient compared to, say, a good data analyst who knows the schema and writes one perfect query.
Oh, it is inherently inefficient. And that high volume, that sort of scattergun approach, it's a massive departure from the workloads we're used to.
The targeted queries from humans or applications.
Yeah. And that inefficiency, plus the sheer volume, that becomes the new performance bottleneck. The whole system chokes because it assumes queries are precise human-crafted things.
Okay, let's zoom in on that volume. The first characteristic, scale. This is where it gets kind of mind-boggling, right? How much throughput are we actually talking about?
We're definitely not talking human scale, maybe a few dozen queries an hour. No. Sources suggest a single LLM agent could potentially hit hundreds, maybe even thousands of requests
Yeah.
per second.
Per second for one agent.
And crucially, that scales up. If you throw more agents at a task, the request rate pretty much multiplies.
Wow. Okay, let's make that concrete. The coffee bean problem example you mentioned earlier, how does that illustrate the scale?
Right, so imagine you task an army of these agents with a business problem. Figure out the technical reasons why coffee bean profits suddenly tanked in, say, Berkeley last quarter.
Seems like a defined problem.
It does, but for that one task, this agent army generates a staggering volume of queries. They're hitting inventory databases, supply chain logs, historical sales data, maybe checking weather patterns, and often they're rechecking the same tables or columns multiple times from different angles.
A lot of those queries must be, well, wasteful, redundant.
Many initial ones are, yes.
Yep.
But that's the cost of getting grounding. They need that context, that basic understanding of what's available before they can even start forming a real hypothesis.
Okay, here's my question, though. If it's so wasteful, why put up with it? Shouldn't the goal be to make the LLM smarter so it asks fewer questions?
Ah, but here's the twist. That high throughput, it's actually, it seems, beneficial for the agent's accuracy.
Really?
Well, studies are showing that this agentic speculation process, this high volume exploration, whether you do it one query after another or many in parallel, it significantly boosts the chance of getting the right answer. We're seeing success rates jump by like 14% up to even 70% in some case studies, just by letting the agents explore broadly.
So the volume helps them self-correct and kind of stumble upon the right path eventually.
Kind of, yeah. It lets them triangulate, discard bad paths, reinforce good ones. The volume isn't just noise, it's part of the reasoning process for the agent.
Okay, so the takeaway is the system has to adapt to this way of working. We can't force the agent into the old model. We need infrastructure that expects this necessary flood of potentially inefficient queries.
Precisely. It becomes the standard operating procedure.
Yeah.
And that naturally leads us to the second characteristic, heterogeneity.
Right.
Because you have such high volume.
Requests aren't all going to be the same type.
Exactly. They vary wildly. It's not a neat linear process. The speculation traces jump around.
So what does that mix look like? Simple lookups, complex joins, metadata checks.
It's all of the above, and it's chaotic. You'll see agents doing really coarse-grained exploration, list tables, describe columns, get basic stats, and then suddenly pivot to trying out a complex piece of logic, a partial solution attempt.
And they can make progress even if the results aren't perfect at first.
Yes, that's key. They can often work with approximate or incomplete answers, especially early on, to just get a feel for the data landscape before committing to heavy computation.
And when researchers looked at the traces, the logs of what these agents do,
Yeah, you see a general pattern. Start with metadata exploration, kind of figure out what's there, then move towards formulating actual queries, the solution. But importantly, those phases aren't clean steps.
they overlap constantly.
Absolutely. An agent could be halfway through writing a complex query, then suddenly realize, oh, this column I need has a lot of nulls. Bang. It jumps back to exploration mode. What's the distribution of nulls in this column? The database has to handle that rapid context, switching seamlessly. High-level exploration 1 millisecond, deep computation the next.
Okay, so this exploratory nature, this messy process, it actually creates an opportunity, which is characteristic 3, steerability.
Right. Because it is exploratory, the data system doesn't have to just passively execute whatever query it gets,
Yeah.
even if it looks like a terrible idea.
It can be proactive, guide the agent.
Exactly. Move beyond just query answer, query answer. Steerability means the system can provide grounding hints, maybe some auxiliary information, before the agent wastes cycles on a bad path.
And this actually works. Giving hints helps.
Massively. When systems inject these kinds of hints of relevant context for the task at hand, the efficiency gains are substantial.
Let's talk numbers again. The study showed. What was the reduction?
Overall, providing grounding hints dropped the average number of queries needed by over 20%, which is pretty significant.
More than 20%. That's huge.
I think it's better. If you look specifically at one type of agent activity, basically, attempting part of the query, which often means trying code that's likely to fail or be redundant, that specific activity dropped by nearly 37% when hints were available.
Almost 40% less wasted effort on those partial, often doomed attempts, because the system nudged the agent away from it early.
Precisely. It prevented the agent from going down a known dead end.
Fantastic. But how does this work mechanically? The agent can't just send a standard SQL query and expect a hint back, can it?
No, it requires a totally new kind of interface. The agent sends something more like a probe, not just a raw query.
A probe, what's in that?
Well, it includes the technical query, sure, but also this natural language brief.
A brief, like instructions.
Kind of. The brief explains the agent's goal, its current intent, am I exploring or trying to solve, maybe what phase it thinks it's in, and crucially, what level of approximation is okay for the answer right now.
Ah, so it gives the database context.
Exactly. All that background info allows an internal component in the database, let's call it a probe interpreter agent, to really optimize the execution, maybe even suggest alternatives before it even touches the data. It gives the database the context that the LLM agent itself lacks.
Okay, that makes sense. Moving on to the fourth characteristic, redundancy. This feels like where we might claw back some efficiency from that massive scale.
It's probably the biggest opportunity, yes, with this huge volume and all the back and forth exploration.
There must be tons of overlap, agents trying similar things.
Huge overlap, both within a single agent's attempts and especially when you have multiple agents working in parallel. We can actually quantify this.
How much redundancy are we talking?
Well, in studies looking at parallel agent attempts on the same task, they analyze all the little computational steps, the subplans or sub-expressions, inside the queries. The number of unique, distinct steps was often a tiny fraction, like less than 10 or 20% of the total number of steps executed across all agents.
Wait, hang on. So if you have, say, 10 agents trying 10 different ways to solve our coffee bean problem, 80% or even 90% of the actual computational work they do under the hood is the same stuff, repeated.
That's what the data suggests. It's an astonishing level of overlap, which, is computationally wasteful if you execute everything naively.
But it's a huge optimization opportunity.
Exactly. It means we can't just rely on old-school query optimization. We need new techniques, things like satisficing probe optimizers that can leverage this redundancy. They extend classic ideas like multi-query optimization, materializing common results, using approximate query processing to satisfy the agent's need without necessarily running every single redundant calculation.
Satisficing the probe, not necessarily executing the query perfectly.
Right. good enough for the agent's current goal.
Mm.
And to make this work across time, not just within one batch of queries.
You need memory, some way to remember what's already been calculated or discovered.
Absolutely. You need a persistent, queryable agentic memory store. Think of it like a super smart cache, but it holds more than just raw results.
What else does it hold?
Results of prior probes, yeah, but also partial solutions that might be useful later, semantic metadata, things like this column uses this encoding, or we know these values are often missing. It stores the grounding the agents have already discovered.
So the system remembers, preventing the agent from asking the same dumb question twice or repeating a failed approach.
Exactly. It stops the agent or other agents from making the same mistakes or rediscovering the same facts over and over.
Okay, this leads us to maybe the trickiest part, state and transactions, especially when agents need to explore what-if scenarios. Let's use that flight crew example.
Right, the delayed flight.
Yeah.
An agent needs to find a new crew. This isn't just reading data, it's inherently transactional and speculative.
It has to consider hypotheticals.
Tons of them. What if we assign crew A? Check their availability, their flight time limits, maybe union rules. Okay, that works. But what if crew B is actually closer? Let's explore that branch. It involves potentially updating multiple systems, hypothetically crewing, schedules, maybe even maintenance testing the outcome, and only committing one final answer.
And agents are aggressive explorers here.
Extremely. Compared to a human doing this, agents might explore, say, 20 times more hypothetical branches, and because many branches lead to dead ends,
They perform way more rollbacks, undoing the hypothetical changes.
50 times more rollbacks, according to some analyses. Traditional databases, built on strict isolation and assuming linear, mostly successful transactions, just aren't designed for this.
They can't handle that level of just massive speculative forking and failing.
Not efficiently. They assume one transaction happens, it's isolated, it probably commits. They aren't built for thousands of simultaneous, hypothetical mini-transactions, most of which will be aborted almost immediately.
Okay, for listeners maybe not deep in database internals, what's the core difference? We have things like MVCC now for isolation. Isn't that enough?
Great question. So, traditional isolation, like multi-version concurrency control, it's mostly about ensuring concurrent transactions see consistent snapshots. It keeps different users from tripping over each other's changes, maintaining one consistent view of history, maybe with a few parallel branches.
But agentic speculation needs more.
It needs what's being called multi-world isolation.
Multi-world. So managing thousands of simultaneous hypothetical timelines.
Kind of, yeah. Think of each speculative branch, each what-if scenario, as a separate world. These worlds need to be logically isolated. The agent can't mix up data between its crew A hypothesis and its crew B hypothesis.
But physically.
For efficiency,
Physically, they need to overlap as much as possible in memory and storage. If 99% of the data in the crew A world and the crew B world is identical, like the base flight schedule, you absolutely do not want to store two full copies. You only store the differences.
that sounds computationally intense.
Yeah.
Managing all those forks and differences.
It requires a redesigned shared transaction manager, yes, with really efficient mechanisms for this massive parallel forking like MVCC on steroids, optimized for huge fan-out, and critically,
The rollback problem.
ultra-fast rollbacks. Because rollbacks are maybe 50 times more common than commits in this workload, you need to be able to instantly abort a failed speculative branch without massive I/O overhead. You have to exploit the similarity between snapshots to discard hypotheses almost instantly. Wow. Okay, this has really been a deep dive. It feels like this agentic shift is forcing a complete rethink, a renaissance almost, in data systems.
I think it is.
So just to recap the 4 big levers we talked about. Scale, the sheer massive throughput needed for agents to be accurate. Heterogeneity, that chaotic mix of exploration and solution-finding queries. Redundancy, the huge 80% plus overlap that offers big optimization chances. And steerability, the ability for the system to actually guide the agent.
And if you tie that all together, the big takeaway is that the database can't just be a passive order taker anymore, just waiting for SQL. It has to become more active, more like an experienced data engineer itself.
How so?
It needs to provide those real-time cost estimates we talked about, offer grounding feedback, maybe using internal optimization tools, you could call them sleeper agents, to steer the LLM before it even asks the really dumb or expensive question.
So the database itself starts participating in the reasoning process, not just executing commands.
That's really the core of it. Which leads to, I think, a pretty interesting final thought for you, the listener, to mull over.
Go on.
If the data system is now actively providing hints, estimating costs, essentially influencing the agent's path and decision-making. What are the implications? Architecturally, sure, but maybe even philosophically. What does it mean when the database itself has a hand in shaping the final answer the AI provides?
Interesting. Giving the infrastructure influence over the outcome. Definitely something to think about. Food for thought until the next time you join us for the deep dive.